Amazon is one of the companies that invented modern microservices. They literally wrote the internal policies that spread this architecture across the entire tech industry. So when Amazon's own Prime Video team published a case study showing they had scrapped their microservices setup and moved back to a monolith, cutting costs by 90% in the process, the software world paid attention. That story is not about microservices being bad. It is about something more important. It is about understanding what each type of architecture is actually for, when it helps you, and when it quietly becomes your biggest problem. Today, we are going to break down the 3 architectural styles that every developer needs to understand: the traditional monolith, the modular monolith, and distributed systems. By the end, you will know exactly which one fits which situation, and how to avoid the most dangerous trap in between. When you build a piece of software, one of the most important decisions you make, often without realizing it, is how to structure it. That structure determines how easy it is to add features, how it scales when millions of people use it, how quickly your team can ship changes, and how much it costs to run. For most of computing history, the answer was straightforward. You built a monolith. Then microservices arrived in the 2010s and became the fashionable answer to everything. Now in 2025, the industry is doing something it rarely does, admitting it overcorrected. A wave of companies are rebuilding the boundaries they drew too early, discovering that the modular monolith they skipped was often the right answer all along. Let us start from the beginning. A monolith is a single deployable unit. All of your application's code, the user interface, the business logic, the database access layer, lives together in one codebase and runs as one process. Think of it like a single building where every department works in the same structure. The sales team, the engineers, the finance team, they all share the same hallways, the same heating system, the same front door. Getting things done is fast because everyone is close together. You do not need a phone call or a network request. You just walk down the corridor. This is exactly why monoliths dominate early-stage development. A single codebase is simple to understand. There is no network between components, so there is no network latency. Testing is straightforward because everything runs in the same environment. Deployment means pushing one thing to one place. For a small team building fast, there is nothing faster than a well-built monolith. Shopify is a monolith. Their Rails application has run with thousands of concurrent developers and handles billions of transactions every year without microservices. GitHub is also effectively a monolith, structured carefully to stay manageable at scale. These are not examples of teams that have not got around to modernizing. These are deliberate architectural decisions made by some of the best engineers in the world. So, what is the problem with monoliths? As the codebase grows, the building starts getting crowded. Every team is stepping on every other team's changes. A bug in the payments module can bring down the search page. You want to scale up one feature because it has more traffic, but you cannot. The whole application is one unit, so you have to scale all of it together. The code that once fit in one developer's head now requires an entire organization to navigate. Small changes require big releases. Big releases mean big risk. This is where the problems start, and where developers typically reach for a solution. The most underused and underappreciated architecture in software development is the modular monolith. And in 2026, it is finally getting the respect it deserves. A modular monolith is still a single deployable unit. You still ship one application. But inside that application, the code is organized into clearly defined, independently evolving modules with strict boundaries. An orders module, a payments module, a shipping module. Each one owns its own data, exposes a clean interface, and communicates with other modules through defined contracts, not by reaching directly into each other's code. Here is the key thing that makes this so powerful. Communication between modules happens in memory. There are no network calls, no timeouts, no data consistency puzzles, no infrastructure to manage. You get the speed and simplicity of a monolith, but with the clear boundaries that let your team scale in terms of organization and codebase without stepping all over each other. Gusto, the payroll platform, uses a modular monolith with domain-driven design. Shopify's internal structure uses modules, like orders and payments, with isolated concerns. Even the concept has a famous advocate. Kelsey Hightower, one of the most respected voices in infrastructure engineering, has said to start with a modular monolith and let it evolve. The modular monolith also acts as a migration path. Because each module already has a clean boundary and a well-defined interface, extracting a module into an independent service later is straightforward. You are not untangling spaghetti. You are lifting out something that was already designed to stand on its own. So if the modular monolith is so good, why did the industry skip it? Because microservices promised even more: independent deployment, independent scaling, technology freedom. And for the right situation, that promise is real. But the situation where it is real is rarer than many teams assumed. A distributed system is an architecture where different components of your application run as separate processes, often on separate machines, communicating over a network. Microservices are the most common form of distributed system in modern software. Each service is responsible for one specific capability. One service handles orders, another handles payments, another handles notifications. Each service can be deployed independently, scaled independently, and even written in a completely different programming language. Netflix is the textbook example. Netflix runs thousands of microservices, deployed independently by hundreds of autonomous teams. When you press play on a film, dozens of services coordinate to deliver that stream: recommendation service, playback service, billing service, device service. Each one can be updated or scaled without touching the others. This level of independence is essential when you have hundreds of developers shipping changes every day. The genuine advantages of this approach are real. True independent deployment means one team can release without blocking any other team. True independent scaling means you can add more capacity exactly where demand is highest without paying for it everywhere else. True technology flexibility means you can pick the right tool for each specific job. But distributed systems come with a cost that many teams severely underestimated. Every service call is now a network call. Networks fail. Networks are slow. Networks introduce latency that does not exist in a monolith. You now have to think about timeouts, retries, circuit breakers, and what happens when service B is unavailable when service A needs it. Data consistency becomes much harder because data is spread across multiple services with their own databases. Debugging a problem that spans 3 services is dramatically harder than debugging a function call. You need distributed tracing, log aggregation, service discovery, and an entire operations practice that simply does not exist in a monolith. And this is where many teams built something they did not intend to build. There is an architecture that combines all the downsides of a monolith with all the downsides of microservices, while delivering the benefits of neither. It is called the distributed monolith, and it is extremely common. Here is how teams fall into it. They split their code across multiple services, but they never fix the underlying coupling. Service A calls service B synchronously. Service B calls service C. They all share the same database. When you deploy service A, service B breaks. When you update the database schema, 3 services stop working. The services look independent from the outside, but behave like a single, tightly coupled system on the inside. You now have all the operational complexity of a distributed system, network calls, deployments, monitoring, with none of the independence that made it worth doing in the first place. The distributed monolith is what you build when you split a monolith by deployment unit rather than by domain boundary. The lesson is not to avoid distributed systems. The lesson is that distribution does not create good architecture. Good domain boundaries create good architecture. Distribution just makes those boundaries explicit. Prime Video's team built a distributed system that hit a hard scaling limit at 5% of expected load and cost too much to run. When they moved the components into a single process, eliminating the network calls and intermediate storage, costs dropped 90% and performance improved. Distribution was the wrong tool for that specific problem. So how do you choose? Start with the simplest architecture that solves your current problem. For most teams building a new product, that is a well-structured monolith. As complexity grows, enforce module boundaries and let it become a modular monolith. That gives you clean code, fast communication, and an easy migration path for later. Move to distributed services only when you have a specific, concrete reason. A team that needs to deploy independently, a component that needs to scale at a fundamentally different rate, a part of the system that genuinely benefits from a different technology. Not because microservices are modern, not because Netflix uses them. Architecture is not a religion, as Amazon's own chief technology officer put it. It is a tool. The right tool depends on your problem, your team size, and where you actually are in your product's life. Start simple, build with boundaries, and evolve only when the domain demands it. Which architecture is your current project using? And do you think it is the right one? Leave your answer in the comments. And if you want to go deeper on system design, the next video on database scaling strategies builds directly on what we covered today.